Hello class. In last lecture we have started a transformer. In that we seen a transformer, working principle of a transformer. Transformer is a static device. There is no moving element or moving part in the transformer. And the working principle is based on the phenomenon of mutual induction between two coils, primary and secondary. Also we are up to the classification of transformer based on their output, step up and step down. We are moving towards a classification of a transformer based on core construction, types of a transformer based on core construction. Transformers are classified into two types in manner in which the windings are taken place around the core. These types are core type and shell type transformer. We first see a core type transformer. Figure shown here is a core type transformer in which on both sides of core, that is on the limb, on two legs of transformer, core type transformer, the windings are wounded in such a manner that low voltage insulation and high voltage insulation is provided in between low winding and high voltage winding. The features corresponding to this type of a transformer, that is a core type of transformer, are: a transformer is built of lamination of a rectangular frame. This is a rectangular frame, and here the lining shows that these are not a continuous material, but it is a laminated sheet which combine together to form a single magnetic circuit. The windings are normally cylindrical in the form and concentric, with low voltage winding being placed near to the core. Both the windings, means high voltage winding and low voltage windings, are uniformly distributed over two limbs, two limbs of a core as shown in the figure. These windings surrounded considerable portion of the core. That's why it is named as core type transformer. Since the windings are distributed on two limbs, natural cooling is more effective. The coils can be withdrawn for repairing just by dismantling lamination of the top yoke. This is an easy feature, or this is a considerable feature while in the point of maintenance. Okay, all these theories are written over here as we talk about. Now the next type is shell type transformer. In shell type transformer, the core of a transformer provided double magnetic circuit. Okay, the windings are normally sandwiched between which is placed on a central part of a limb. That's high voltage and low voltage coils, which are wound in the form of like pancakes, and it is interweaved. The top and bottom coils, which near the yoke of the core, is of low voltage winding only. टॉपला आणि बॉटमला फक्त लो व्होल्टेज वाइंडिंग्स असतात, मध्ये या लावलेले असतात ॲज लाईक इन दिस फिगर. प्रायमरी आणि सेकंडरी असं म्हणायचं त्यांना. हे कोड आहे. इथे काय होतं तर सेंट्रल पोर्शनला आहे, जास्तीचा पोर्शन शेल टाईपमध्ये कव्हर केलेला नाही, आणि जसं इथे सांगता येतच त्याप्रमाणे हे घेतात बाबा जास्तीचा पार्ट असं म्हणूया. इन दिस ऑल्सो coils are former wound but area of multi-layer disc type coils which are wounded in the form of pancakes. These multi-layer disc coils in different layers are separated by each other by paper. The whole winding consists of stacked disc, and in between the coils the insulation space is provided. Insulation, self-insulation is provided. Berry transformer is the most commonly used shell type transformer. In shell type, core has 3 limbs and the windings are wound around the central limb. 3 limbs म्हणजे कसं झालं बाबा, 1, 2 and 3 मधल्यावरती झालेले. लिम्स म्हणजे पाय असं तुम्ही म्हणू शकता. तीन पाय आहेत ह्या कोरला असं म्हणा. ठीक. बोथ लो व्होल्टेज अँड हाय व्होल्टेज वाइंडिंग्स आर डिवायडेड इंटू द डिफरंट कॉइल्स विच आर अरेंज्ड अल्टरनेटिव्हली. लो व्होल्टेज आणि हाय व्होल्टेज अल्टरनेटिव्हली केलं तर तरीसुद्धा टॉप आणि बॉटमला मात्र लो व्होल्टेज वाइंडिंग्सच प्रेफर केले जातात, ज्या की मेंटेनन्सच्या वेळेला खूप कामाला येतात. ठीक आहे. नाव द नेक्स्ट टाईप इज बेस्ड ऑन द नेचर ऑफ सप्लाय. डिपेंडिंग अपॉन द नेचर ऑफ सप्लाय, ट्रान्सफॉर्मर इज classified as a single phase transformer and three phase transformer. Okay, transformer can be single phase and three phase. Single phase transformer are designed to work on the single phase system only. Therefore, it has two windings to transform the voltage levels. These are used in remote ends of the power distribution system. जिथे हलवता येतं किंवा जिथे साईज कमी आहे, पॉवर हँडलिंग कॅपॅसिटीज कमी आहे. These have less power rating compared with a three-phase transformer. Yes, mostly core type construction is used for single-phase transformer. To work with three-phase system, we need three single-phase transformer. Thus, for an economic advantages, three-phase transformer is considered for three-phase operations only. It consists of three windings or three coils which are connected in a proper way to match the input voltages. This type of transformer, primary and secondary windings are connected in the form of star delta or delta star fashion depending upon the load voltage requirement. The figure over here is a single type, and the next figure, this is a three phase, phase R, phase Y and phase B. Okay. Based on their use, transformer as classified as power transformer. Second is distribution transformer, only for the distribution purpose, and instrument transformer. Their name itself suggests where they can use. Other type of transformer, based on the type of cooling system they preferred, is self air cooled transformer, air blast cooler transformer, oil filled self cooled transformer, oil filled water cooled transformer, oil filled force oil cooled transformer. These are the types enlisted for a transformer. Now we will see the e.m.f equation of a transformer. In a transformer, source of alternating current is applied to the primary winding. We know that the windings which are subjected to the AC input source are called primary winding. Due to this AC voltages, the current in the primary winding, called a magnetizing current or self-magnetizing current, produces a self-alternating flux in a core of a transformer. This alternating flux gets linked with the secondary winding, and because of the phenomena of mutual induction and induced e.m.f is get induced in the secondary winding. Magnitude of this induced e.m.f can be found by using the e.m.f equation of a transformer. Let's see the e.m.f equation of a transformer by reference of the AC input cycle, which we get an e.m.f by Faraday's laws of electromagnetic induction. There also we stated E is equal to n d phi by dt, where n is a number of turns of the coil, and d phi by dt rate of change of flux linkage with a primary and secondary. Let now n1 are the numbers of primary winding, n2 number of turns in the secondary winding. Likewise, phi m is the maximum flux in the core, which is given in Webers, and the flux density or maximum flux density Bm, which is equals to phi m by A. So we could write phi m is equal to Bm into A area of cross section, where f is the frequency of a AC input cycle in Hertz. Now, as shown in the figure, the flux rises sinusoidally. This is the sinusoidal waveform from 0 up to the maximum value. Here maximum value is phi m. Suffix m represents this is the maximum value of input at angle 90. We've seen that. It reaches to the maximum value in 1/4 of the cycle. that is t by 4 seconds, where t is a time period of the sine wave of a supply. So t could be written as 1 by f. Therefore, average rate of change of flux, which is equals to flux phi m, maximum flux phi m, divided by a time period t by 4. So we can rewrite at this one by replacing t is equal to 1 by f. So phi m upon 1 by 4 f in terms of frequency. We get this one. Now average rate of change of flux, which is equals to 4 f phi m Webers per second. Induced EMF per turn, which is equals to rate of change of flux per turn. Therefore, average EMF per turn, which is equals to 4 into F into Fm volts. Now, we know form factor, which is equals to RMS value divided by average value. The formula for form factor. Therefore, RMS value of EMF per turn, which is equals to form factor into average EMF per turn. As the flux phi varies sinusoidally from a factor of sine wave, which is constant 1.11. Therefore, RMS value of EMF per turn should be written is 4f pi m multiplied by 1.11, which we resulted in 4.44 f times phi m. RMS value of induced EMF in the whole primary winding is E1, which is given by RMS value of EMF per turn into number of turn in the primary winding. Absolutely correct. So we could return E1 primary EMF or EMF induced in the primary, which is also called a self-induced EMF, as it is connected to the AC input signals, which is equals to 4.44 f into n1 into phi n. We can treat it as equation 1. Similarly, RMS values induced EMF in secondary windings, that is E2 EMF in secondary, which is mutually induced EMF, can be given as E2 is equal to 4.44 f into n into phi n. We treat it as equation 2. From equation 1 and equation 2, we can evaluate E1 upon n1, EMF of primary divided by number of turns of a primary, which is equals to EMF of secondary divided by number of turns of a secondary, which resulted into 4.44 f into phi m. This is called EMF equation of a transformer, which shows the EMF by number of turns is the same for both primary and secondary winding. For an ideal transformer where there is no load, E1 is equal to V1 and E2 is equal to V2. Means EMF of across primary, which is equals to the primary voltage, and EMF across secondary, which is equals to the secondary voltage, where V1 supply voltage of a primary and V2 is a terminal voltage of a secondary voltage. The voltage transformation ratio given by K as derived from E1 upon N1, which is equals to E2 upon N2, which is equals to a constant K. This constant K is called voltage transformation ratio, and we can now given as if N2 is greater than N1, means secondary windings are greater, number of turns are greater than N1, that is K is greater than 1, then the transformer is called step up transformer, otherwise it should be step down transformer. Okay, now we will see a current ratio. I already shared this PDF with you. Current ratio, since the transformer transfer electrical power from one circuit, means primary to the secondary, very efficiently with a negligible power losses, therefore power input is equal to power output. We can given it as V1 into I1 into cos of phi 1 primary, which is equals to I2 into V1 into cos of phi 2. V1 voltage of primary, secondary we do not connect it to the input sources, so we also taken a V1. We know P power is equal to Vi into cos of phi. where I1 and I2 are the currents in the primary and secondary circuit respectively, and cos phi 1 and cos phi 2 are the corresponding power factors. But a transformer, the primary and secondary power factors are also nearly equal, particularly at full load. That's why we can write it as V1 into I1, which is equals to V2 into I2. So we could get I1 upon I2, which is equals to V2 upon V1. Combining the results, we can get equation V2 upon V1, which is equals to I1 upon I2, which is equals to N2 upon N1, which is equals to K, and this expression is called a current ratio. It means the ratio between the primary current and secondary current. As like the voltage, V2 upon V1 is a voltage ratio. Likewise, I1 upon I2 is a current voltage. But in current voltage, the relation is I1 upon I2 which is equals to V2 upon V1, not V1 upon V2. It is equals to V2 upon V1, which is equals to